Howdy. We're going to be talking this evening about how to find the area between curves. And the actual math is fairly simple, but there are a couple of things that we're going to need to make sure that we do in order to be careful problem solvers. So I'm going to try to emphasize those things as we go through. We're going to be taking a look, if you have your book, on page 395. We're going to be looking at numbers 1 and 4. We're also going to take a look at numbers 10 and 13 as more advanced examples. In problem number 1, they ask us to find the area of the shaded region analytically. And the region that we have is defined by two curves here. And one curve is the curve y equals 1, and the other curve is the curve y equals cosine squared x. These two curves are called bounding curves. They give us an additional point here, pi over 2. And the shaded area that we're looking at is this guy right here. So these two curves are called bounding curves, and they define the region R that we're looking for. R is this guy that is bounded by these curves right here. And the first thing that we need to do in order to be careful is that we need to identify the intersection points of our bounding curves. And to do that, we're going to set the bounding curves equal to each other, the y-coordinates equal to each other. So that we will know the extent to which these guys extend. Now, you probably have guessed from the graph, excuse me, already. Or you can do a little bit of factoring. And if we set cosine x equal to 1, then the solution in the first quadrant is going to be x equals 0. And that gives us the point 0, 1. Notice that all the y-coordinates had to be 1, of course. And if we set cosine x equal to -1, then we get x equals pi, which is this fellow right here. And so we have found our intersection points. We're going to use those intersection points crucially in just a moment. Now what we're trying to do is to find the area, and so that suggests that we need a Riemann sum. And to construct our Riemann sum, we are going to take and divide up the region into, or we're going to approximate the region with a large number of rectangles. And these rectangles can be either vertical rectangles or they can be horizontal rectangles. If they are vertical rectangles, then their width is going to be dx, and their height is going to stretch from the top curve down to the bottom curve. In other words, the height is going to be top curve minus bottom curve, which is going to be 1 minus cosine squared x in this particular case. If we choose horizontal rectangles, then the width of the rectangle is going to be dy, and the the length of the rectangle is going to be the right curve minus the left curve. Here in this particular case, it's not very convenient to do horizontal rectangles, so I'm actually going to postpone until the next problem, showing how that works out in this particular case. Here, it's pretty obvious that we want to do vertical rectangles, and the reason for that is simple. Both of my curves are given to me as functions of x. And because both my curves are given to me as functions of x, it is natural for me to want to work in the x variable. And in order to do that, I have to have a width of dx, which means I need to use vertical rectangles. If I'm working with vertical rectangles, then the area is then going to be the integral from the first x to the last x of top curve minus bottom curve dx. Notice that the top curve, I need to, in my particular case, since I labeled 1 as the top curve, and as f of x, I need to make that top minus bottom. Well, this is fairly simple and straightforward then. I've drawn myself one of the many, many rectangles that cover this region. I'm going to take just this one here, and this guy right here, which is this guy right here, is my representative rectangle. He represents all of the different rectangles for different values of x. And you can check that we have the right height when x is equal to 0 out at the end right here. Then my height is 0, which is appropriate for this representative rectangle. And when x is pi, I also get 0, which is appropriate. And when x is equal to pi over 2, I get a distance of 1 minus 0 is 1. And so I've done this right. The area is now the integral from the first x to the last x of top curve minus bottom curve, just like so. And I'm happy with everything except one small thing, and that is the integral of cosine squared x dx. Well, some of you may be saying, wait, I know. I can replace 1 minus cosine squared x with sine squared x, and that's true. But we wonder how that helps us. In order to integrate either cosine squared or sine squared, we're going to appeal to the double angle identity. You may recall that cosine of 2x has 3 different representations. One is cosine squared x minus sine squared x. One is 2 cosine squared x minus 1. And one is 1 minus 2 sine squared x. These representations actually allow us to integrate cosine squared and sine squared by rewriting them in terms of cosine 2x. And this gives us the double angle identities. If I solve in the first case, I find that cosine squared x is equal to cosine 2x plus 1 divided by 2. And if I solve in the second case, I find that sine squared x is 1 minus cosine 2x all over 2. For reasons of symmetry, it kind of makes sense to rewrite this as 1 plus cosine 2x. So since we have this representation, I can immediately replace sine squared x with what it is, or 1 minus cosine 2x all over 2 dx. And now we can integrate a term at a time. This is the integral from 0 to pi of 1/2 minus the integral from 0 to pi of 1/2 cosine of 2x. This integral is obviously pi over 2. This integral right here, I could do it analytically, but I'm going to cut to the chase and say that this integral is 0. Why? Well, because cosine 2x is a function that is periodic with a period of pi, and when I integrate from 0 to pi cosine 2x, all of the positive area here and the negative area here cancel out, giving me 0. So I immediately have pi over 2 as the value of the area between the two curves. Let's consider the second problem, number 4, on that same page. And here in problem number 4, we are given a region that is bounded by two curves that are functions of y. First curve stretches out like so, and it has the equation x equals 12y squared minus 12y cubed. And the second curve looks like so, and it has the equation x equals 2y squared minus 2y. And so now we wish to find the area of the region that is defined, that is bounded by these curves. In this particular case, it seems obvious that I would want to use horizontal rectangles. And the reason for that is that my two bounding curves are given as functions of y. And so if I paper this region with rectangles whose height is dy, I get to work in the variable y, and that makes a whole lot of sense. But it does mean I need to find the intersection points, and so here we go. We're going to set the two curves equal to one another, and when we do, then we get the equation 0 equals negative 12y cubed minus the plus 10y squared plus 2y. And if we now factor out a y equals 0, excuse me, a factor of y and a factor of 2, then we get this fellow right here. It's kind of an odd factorization, but I think it's pretty clear that we're going to need plus 1 plus 1, and I think it's also fairly clear that we're going to want to have 6y here and negative y right here. And this gives us 3 solution points. Which ones am I going to choose? Well, it seems fairly clear that the ones that we're interested in are y equals 0, which is where x equals 0 also, and y equals 1, which is where x equals 0 as well. And so now that we have done this, we're going to consider the width of our rectangle, and the width of our rectangle is going to be the right curve minus the left curve. That is, this is my representative rectangle here, and its width is this guy right here. And it can be simplified, but I'll do that in the integral in just a moment. So now we're ready to set up our integral. And the integral is going to be the area from the very first y value out to the very last y value of right curve minus left curve. dy. Please notice that we used y values in setting up our integral as we are integrating in this direction. We're integrating upwards from 0 to 1. We're adding up rectangles of various lengths. Well, now this is a simple polynomial. And so to simplify this, we have 10y squared minus 12y cubed plus 2y dy. Notice that this polynomial that we are integrating is exactly the same as the polynomial that was equal to 0 before, and that must always be the case. And so this gives me 10 thirds y cubed minus 12 fourths y to the fourth plus y squared from 0 to 1, which is equal to 10 thirds minus 3 plus 1, or 4 thirds. And that's it. So the use of horizontal rectangles is fairly straightforward. The key to making it work is to draw your representative rectangle and to recognize that the width of your rectangle is going to be right curve minus left curve. In this case, the use of y was obvious because both of my widths were given to me in terms of y. I wish to now consider a situation that is ambiguous. Page 396, number 10. And on page 396, number 10, we are given a region that looks like this, and it's bounded by three curves. One is the curve y equals x squared. One is the curve x plus y is equal to 2. You say, where is the third curve? The third curve is the x-axis, y equals 0. Without that bound, then the region would extend down infinitely, and we would have no finite answer. So now the question is, if I wish to find the area of the region here, should I use horizontal rectangles or vertical rectangles? Let's consider the pros and cons of each. If I use vertical rectangles, then my representative rectangles run into a small problem. Here's one representative rectangle right here. Here's another one right here. And if you'll allow me to label these 1 and 2. Vertical rectangle number 1 has a width of dx, and it has a height of x squared minus 0, top minus bottom. Meanwhile, vertical rectangle number 2 has a width of dx and a height that is the top curve, that is y equals 2 minus x, minus the bottom curve, which is 0. So I do not have the same expression for the height of my rectangles for all of the rectangles that are to the left of this line right here. The height is x squared. And for all the rectangles that are to the right, the height is 2 minus x. And that means that if I were to set this up in terms of x, I would have to use two separate integrals to make it happen. And in fact, I would need to find the intersection point. I think it's pretty clear that the intersection point is going to be 1, 1. But if you're not sure about that, you can set the two curves equal to each other. And factoring is your friend. So, if the area, so if we have the intersection point 1, 1, then my area would have to be represented in terms of two different intervals. From 0 to 1, my height is x squared. From 1 to 2, notice that the intersection point here is 2, 0. From 1 to 2, my height is 2 minus x. And then we could evaluate. Now, there's nothing wrong with this. In fact, the evaluation is pretty simple. We get 1/3 for this integral, and we get 4 minus 2 minus 2 minus a half. And when the dust settles, that's 1/3 plus 2 minus 2 is 0 plus a half, which is going to be equal to 5/6. Notice that the half here is an expected value for this integral because I have a nice little isosceles right triangle with a length of 1 and a height of 1. So that's perfectly fine. But what if I were to do horizontal rectangles instead? If I do horizontal rectangles, now something really nice happens. Let me make a copy of our curve so that I'm not making it too messy. If I do horizontal rectangles, then the width of, or the height of each rectangle is dy. The width of each rectangle is going to be right curve minus left curve. In other words, it's going to be this curve minus this curve, and that's true all the way up, so that I have only one integral to evaluate. Well, what is the right curve? What is the left curve? The right curve has to be done in terms of y. So I solve for x in terms of y and get x equals 2 minus y. Over here, I solve for x in terms of y, and I get x is equal to, technically, plus or minus the square root of y. However, it is clear that I'm looking at positive x values for this particular bounding curve. So I'm going to take x equals the square root of y, positive square root of y, as my bounding curve. And now at this intersection point 1, 1, I can read the very last y value. My top y value is going to be 1. My bottom y value is going to be 0. So the area is therefore the integral from 0 to 1 of right curve minus left curve. One simple single integral. And let's see, add 1 to the power, divide by the new power. And this gives me 2 minus 1/2 minus 2/3. And 2 minus 1/2 minus 2/3 is going to be the same as 2 minus 7/6, which is equal to 5/6. Notice it's exactly the answer that we got before. The area of the region is an invariant. No matter how I compute it, it's got to come out to be 5/6. But the horizontal rectangles had the advantage of needing only one rectangle but at the cost of having to solve for x in terms of y. And those are the two factors that you, the smart mathematician, are going to want to consider when you're setting up your areas. Do I wish to have two integrals to represent my area? Do I wish to have to solve for one variable in terms of the other? And those two factors basically become the two things that drive your choice of horizontal or vertical rectangles. We're going to look at one final example problem, and then we are done. I want to take a look at number 13 on the same page. Here we have a very interesting region. And they give us everything. They give us the two curves. Y equals 2x cubed minus x squared minus 5x. And the curve y equals negative x squared plus 3x. And it looks like the curves intersect somewhere over here. And they also give us the intersection points. This one, these two intersect at 2, 2. This intersects at -2 and -10. And I don't think it takes too much imagination to see that this intersection point is 0, 0. The only thing that is slightly strange about this is that the top curve changes identities as we move from -2 to 2. From -2 to 0, my top curve is the cubic. Y equals 2x cubed minus x squared minus 5x. As I go from 0 to 2, my top curve is equal to negative x squared plus 3x. Because of this, it is necessary that I set up two integrals as an evaluation. So the area then is going to be the integral from -2 to 0 of top curve minus bottom curve. And here the top curve is this. The bottom curve, oops, is that, plus the integral from 0 to 2. And now we see the top curve and bottom curve exchanging roles. Like so. This, by the way, is a pain in the neck to evaluate, but it's totally doable. I mentioned that we needed two integrals here, 1, 2. There is a way around that if you happen to have a calculator available to you. If you happen to have a calculator available to you, you can reason that top and bottom don't matter too much. What I'm really looking for is just the distance. And the distance between two things is given by the absolute value of their difference. So the distance between y1 and y2 is the absolute value of y1 minus y2, which is exactly the same as the absolute value of y2 minus y1, which is why absolute value is useful for computing distances. It doesn't care what is top and what is bottom. So we could express the integral, the area, as the integral over the entire interval of the absolute value of one curve, and it doesn't really matter which one, minus the other curve, dx. And we can let the calculator handle that integral for us, and it will be happy to do so. Why is this only suitable when calculators are involved? Well, because if a calculator is not involved, we don't happen to have an antiderivative for absolute value. And as a result, to evaluate these integrals by hand, we need to piece out which curve is top and which one is bottom, and that leads us right back to finding intersection points and expressing the area in terms of two integrals. So when we integrate by hand absolute values, we have to do exactly this process right here.